Okay, this is my demonstration video for my artificial intelligence module. In this C# program, I've implemented an A-star algorithm and a learning real-time A-star algorithm to calculate the shortest path between 2 points on a grid. Now, before we get into what I've programmed for the algorithms, you can first see that I've got a game class here. At the top, you can see that I've created a bot for the A-star algorithm and one for the learning real-time A-star algorithm. I've also, in the constructor, loaded in a map. So this is level 0. We've got 5 maps to go through. And I've also created two types of the coordinates which hold an X and Y position for the bot position and the target position. Here you can see that I initialize both algorithms, and starting with the A star, I call upon a build function within that class which actually implements the algorithm so we can calculate the shortest path. Further down you can see I've got a function for loading the content, unloading it and updating the game. This is where we can actually move the bot around, but we won't actually be using this that much. I've also got two functions which will come important later, especially this one where we actually draw the grid so we can demonstrate the path that the bot is following. Right, so getting into the A star algorithm, first you can see that I've created a node class where we create a couple variables for each node. Each node will have its own parent, it'll have its own coordinate type for the X and Y for the grid position, it'll have its own vertex, and it'll have its own G cost, H cost and F cost. It'll have its own level so that we can calculate the shortest path as well. Right, so moving over to our A star algorithm, first thing to see is we've created a couple more variables here above the constructor. More importantly, we've got two lists. One for all the nodes that need to be explored, and once they've been explored we can then move them over to this visited node list here. I've also created an I directory for the path tracking and a list of coordinates so that it makes it a bit easier for us to draw it. Now the main part of this algorithm is this build function here. You can see that it takes no parameters, but it does return a list of coordinates. So first thing we want to do inside this function is create a new node object called the current node and assign all the variables. So the parent's going to be -1, obviously because it's the start, the node's level, and the node's G cost is going to be equal to 0. We're going to calculate the H cost using a function that I've created below. So the heuristic that we're using is actually the Euclidean distance. So we're just going to be using Pythagoras to calculate the 2 points when they're on the map. Once this is done, we can assign a value to the current node's F cost, and now that this is all done, we can add it to the node list. It's worth mentioning that the format for the I directory string is just going to be the node vertex plus a level, and obviously we've got the node object on the end, so we can add that to the path tracking. The main part of this build function is we've got a while loop which is going to continuously run as long as the node list has got something in it. The only way it's going to break is if we run this if statement and the current node's grid position equals the target. So once that's true, we know that we've calculated the shortest path and we've actually reached the end. What we want to do above that is give a new value to the current node. You can see here above that I've created a get minimum vertex where we're going to basically run through every node in the node list and return the one with the shortest F cost. If this if statement returns false, then we're going to go ahead and carry on with the while loop. So we've got a for loop here which is going to check every node in the identity matrix, and what we're going to do here is we're going to check to see if it's an adjacent node to the current node we're dealing with. If it has a value of 1, it means that the node's either on the left, right, above it or below it. If it has a value of 1.4, it means that the node is diagonal to it, but it's still adjacent. For every adjacent node, we're going to create a new node and assign all the variables. So the level is just going to increment by 1. We can calculate the node's G cost and we can calculate the node's H cost here. Once these are done, we can assign a value to the node's F cost and we can add it to the node list. What I'm going to do below here is just run an if statement again. So if the path tracking doesn't contain the key, we're going to add it to the path tracking. Right after this for loop is finished, we can add the current node to the visited nodes because it's been explored, and we can remove it from the node list here. We then want to reassign the value for the current node, so call upon that function again. So we're going to run through every node in the node list and return the one with the smallest F cost. We're going to run the same if statement here. So if the current node's grid position equals the target, it's going to break the loop as it's reached the target. This while loop here will continue to run until we've reached the target. So eventually, the current node's grid position is going to equal the target. Once this is true, we can break the loop and begin another one right after. Now when we get to this while loop here, we can see that the current node has reached the target. So now we need to go back on itself to calculate the path. We create a temporary node, give it a new key, but we want to be taking one away from that level every time, and we're going to add this to the path to draw list. This adds all the current node's grid position to a list of coordinates for the path. Now if I add a breakpoint in here, just to demonstrate, restart the program. If we look at this path to draw list of coordinates, now we can see that we've got 20 in. These all contain their own x and y. So these are all the points on the graph that add up to calculate the shortest path. Okay, so now that I've explained the algorithm, I'm just going to show it working on all four maps. If we start with the first one, which is the most straightforward, it's just a straight line. You should be able to see that I've calculated the path and coloured it in red to show which is actually the shortest path between the bot and its target. Once it reaches the end, it should stop. There we go. I'm just going to go ahead and change the speed, make it a little bit faster. If we change it to make it the second map, this should have an obstacle. You can see that it's moving diagonally to reach its endpoint. If we put in the third map, try the fourth map there, which should be a little bit more complex. You can see that it finds the shortest path every time. And finally we can try it on the final map, which is the most complicated. You can see it's working its way out of its maze to find the endpoint.